Okay, hello everyone. My name is Todd Alhart. I'll be your host for today's webinar, and the topic is about, hello, and if I could just, for those of you who've dialed in via phone, if you could mute your phones, that would be appreciated. We're going to get the feedback otherwise into the audio. But we've got a great webinar planned for you for this hour on Movement Planner and Trip Optimizer technology developments underway here at GE Global Research. And I have two of our senior scientists here to talk about those initiatives. Srinivas Bola-Pragada, who is a principal scientist in our Software Sciences and Analytics Lab, who's going to talk to you about Movement Planner. And Perry Vanani, who is one of our senior engineers in our Electrical Technologies and Systems organization, who's going to talk to you about Trip Optimizer. So we'll take about 20 minutes each. Srinivas will walk you through Movement Planner first. And then another 20 minutes where Perry will walk through the Trip Optimizer technology. And following that, we'll leave time for questions. So I think plenty of time for some good questions in the hour. And just ask, and I'll remind everybody when we get to the Q&A, but just direct all questions to me, your host, and we'll try to get through as many as we can in the time that we have. So without further ado, let me introduce Srinivas, and I'll turn it over to him.
Thanks, Todd. Hi, I'm Srinivas Bola-Pragada from GE Global Research Center in Helena, New York. I'm pleased to host this webinar with my colleague Perry Vanani. I've been with GE Research for over 16 years. During that time, I had the opportunity to develop a number of innovative algorithms-based software systems and tools that are currently in use within and outside GE. I have a PhD in operations management from Carnegie Mellon University. I was fortunate enough to receive a number of awards for my work over the years, and I currently serve as the editor-in-chief of the Informs journal Interfaces. Let us begin with a brief overview of GE and its Global Research Center. GE was founded in 1892 by Thomas Edison. It is now a global company with over 300,000 employees and operations in more than 100 countries. Around 60% of GE's revenues are from outside the US. The company operates in a diverse set of industries, including transportation, aviation, energy, healthcare, and financial services. The Global Research Center where we work is the central research and development organization that serves the entire company. The center is over 110 years old and is one of the most diverse industrial research labs in the world. Its mission is to bring great technology to the marketplace. The center has 3,000 employees who work from 5 locations around the world. These sites are in Niskayuna, New York, Bangalore, India, Shanghai, China, Munich, Germany, and Rio de Janeiro, Brazil. During the next 20 minutes, I will present our work on Movement Planner. This is joint work with GE Transportation in Melbourne, Florida. My role on this project was to develop the Movement Planner algorithm. A large team at GE Transportation developed the software system that is now in use at the Norfolk Southern Railroad. A movement plan is a detailed plan for moving trains in a rail network over a time horizon of 8 to 12 hours. It is also called a meet pass plan because it involves planning the meet locations where trains traveling in opposite directions can get past each other, and pass locations where a fast train can get past a slower train traveling in the same direction. In addition to meets and passes, the plan includes schedules for activities such as train originations and terminations, crew and engine changes, train stops, and inspections. Currently, dispatchers develop movement plans manually at most railroads. Automating and optimizing this process can significantly decrease operating costs and increase the network throughput of a railroad company. A train graph is a tool for visualizing a movement plan. The track running from one end to the other is represented along the y-axis. The labels on the y-axis are stations along the track. Time is represented along the x-axis. Each line in the graph shows the locations of a single train at various points in time. The upward sloping lines represent trains traveling in the upbound direction, and the downward sloping lines represent trains traveling in the downbound direction. The slope of a line gives the velocity of a train at that point. There are 7 Class 1 railroads operating in North America. Each Class 1 railroad owns between 30 and 60,000 miles of track. They dispatch between 1,000 to 5,000 trains per day. The trains are of different types, which include passenger trains, intermodal trains, commodity trains that carry grain and coal, etc. These trains have different priorities that need to be considered when generating a movement plan. For example, when planning meets and passes, we need to wait low priority trains at sidings while we let the high priority trains go by. The trains are fully controlled by dispatchers sitting in centralized dispatch centers. In each dispatch center, there are a number of dispatchers who control the movement of trains in the rail network. Each dispatcher controls a section of the track and is responsible for the safe and efficient movement of trains in that section. A dispatcher manually plans all activities associated with moving trains over his or her section. The manual dispatching of trains leads to suboptimal operations. A dispatcher focuses only on a small section of the track that he or she controls and does not have a global view of the entire network. Therefore, what looks locally optimal for a dispatcher may harm the network. Moreover, the number and complexity of decisions to be made makes it very difficult for dispatchers to make even locally optimal decisions. As a result, trains may end up waiting for long periods of time at meet and pass locations and may require activities such as crew changes to be performed at expensive locations. Currently, freight trains in North America travel at an average velocity of 20 to 25 miles per hour. Increasing this velocity by 1 mile per hour is expected to save a typical Class 1 railroad over $200 million. Efficient dispatching of trains requires quick generation of near optimal movement plans. Computing a movement plan requires a variety of data on trains, tracks, and required activities. This data includes train schedules, train priorities, operating costs, the topology of the rail network, speed restrictions and track blocks, real-time status of the trains, and dispatcher inputs. A planning algorithm uses all this data to compute a near optimal way to move trains in real time. Because the state of the rail network is constantly changing, the runtime of the algorithm should be sufficiently small, typically under 1 or 2 minutes, so that it can be rerun at frequent intervals. Computing a movement plan is a complex optimization problem requiring a large number of decisions. These decisions include the path that each train needs to take from origin to destination, the meet and pass locations in the planning horizon, the locations where activities such as crew changes need to be performed, etc. A simpler version of this problem can be formulated as a network flow problem. The objective is to minimize the total cost incurred in moving all the trains from their origins to destinations while satisfying all the constraints. Even this formulation for the simpler approximated problem leads to a very large mixed integer program with millions of integer variables and cannot be solved using state-of-the-art integer program solvers. Computing even a good feasible solution for real-world problems using existing techniques is difficult. It is also difficult to capture all real-world constraints in the math program formulation. To comprehend the complexity of real-world problems, let us go through some of the requirements that need to be met in computing real-world movement plans. These requirements can broadly be classified into track-based, train-based, activity, and plan variation requirements. Track blocks, speed restrictions, and switching constraints reduce the capacity of the rail network. These restrictions could be in effect for the entire duration of the plan or for a shorter duration. The planner should meet these constraints when they are in force and should take advantage of the increased network capacity when they are no longer active. Height, weight, and width restrictions limit certain trains from using some portions of the track. A train may be required to follow a preferred route as much as possible and only take an alternate path if it is essential to do so. Some sidings may accommodate multiple trains, while others can only accommodate a single train. Train-based requirements. Train priorities can be static or dynamic. For example, the priority of a train may increase when it is running late or its crew is close to expiration. Order constraints require that trains arrive at a certain location in a pre-specified order. Key trains are those that carry hazardous materials. They should not be made to wait in sidings unless it is absolutely essential. Unplannable trains are local trains shuttling between rail yards and customer locations without published schedules. The algorithm should accommodate for them when they enter the rail network. The planner should schedule a number of different types of activities. Combo train activities are those where two different trains meet at a location and are connected together before proceeding forward as a single train. A linked train activity happens when a train drops off some cars at a certain location to be picked up by a second train. The planner should ensure that the train dropping off the cars arrives at the location first and the second train arrives after a specified amount of time. After that, some trains may not have enough horsepower to get them over hills. A helper locomotive is used to pull such trains over the hump. The planner should schedule the helper engines. The planner should also schedule crew changes, station activities, and off-track activities at specified locations. Sometimes, dispatchers would like to schedule some meets and passes at certain locations. The planner should honor such requests. There are a number of unplanned events that frequently occur on the rail network. For example, trains can be early or late when entering the rail network from rail yards. There can be changes in speed restrictions and track blocks. The train priorities may change. Some trains may be cancelled and new trains may be added. The algorithm should account for these changes and quickly develop new plans when necessary. Variation between two consecutive plans should be as small as possible. We developed a novel heuristic algorithm that exploits the structure of the problem to come up with a good, robust solution in a fraction of a minute. Our goal is not to come up with the optimal solution, but to quickly generate a robust, near-optimal solution that achieves significant improvements of all the performance metrics that are of interest to railroads. Using a detailed model of the track topology, our algorithm systematically constructs the movement plan, starting with the current state and planning forward till the end of the time horizon. We thoroughly tested the algorithm for feasibility and performance using a number of real-world scenarios. The column on the right has the plan-level metrics that we use to measure the performance of the algorithm. These metrics drive the system-level metrics that the railroads are interested in. The algorithm runtime should be less than a minute to enable real-time dispatching. The average train velocity has to be maximized. The number of unresolved conflicts and unplanned trains should both be zero to ensure feasibility. The average number of switches per train has to be minimized to prevent excessive switching between tracks. The percentage of meets and passes retained between successive plans has to be maximized to ensure plan stability. We integrated the algorithm into a computer-aided dispatch system called the Precision Dispatch System, which was developed by GE Transportation's software division located in Melbourne, Florida. The software system keeps track of all the detailed information that is needed to move trains safely and efficiently. It displays this information along with the output of the planner in an interactive user interface that the dispatchers use to control the movement of trains. The system also has the capability to automatically route the trains in real time based on the planner output. GE Transportation implemented the movement planner algorithm and the PDS system at the Norfolk Southern Railroad during 2008. In January and February of 2009, Norfolk Southern performed live tests of the algorithm in its Georgia division on 3 different days. The testing showed that the average velocity increased by over 30% and on-time performance improved by around 25%. Average schedule deviation, crew district transit time, and relief crews required have all significantly improved. Upon completion of this testing, Norfolk Southern rolled out the algorithm across all its 11 divisions. The algorithm is currently being used to auto-route trains in a couple of divisions and is available on an advisory fashion in the rest of the divisions. The average network velocity has gone up by 2 to 4 miles per hour in the divisions that are currently auto-rating the trains based on the algorithm output at Norfolk Southern. Once all divisions auto-route trains, this will translate to operational and capital savings of $400 to $800 million per year for Norfolk Southern. The algorithm improves the capacity of rail network without laying additional track. For example, using Movement Planner, a railroad running 20 trains a day between New York and Washington, D.C. could increase that to 23 trains a day simply by better utilizing the existing track. Given that it costs more than $1 million a mile to lay the track, this technology will greatly reduce capital expenses from more productive use of existing assets. Travel time decrease. A freight train from Louisville, Kentucky to Macon, Georgia that used to take 27 hours for the trip now requires 22.5 hours, saving more than 4 hours of travel time. This results in significant decrease in crew and other operational costs. GE is currently in talks to deploy its Movement Planner technology at other railroads, both in the U.S. and internationally. This concludes my presentation on Movement Planner. My colleague will now talk about Trip Optimizer.
Good afternoon, everyone. My name is Perry Bonanni, or Pierino Bonanni to any Italian speakers that might be out there. I've been with GE since 1991. I'm originally a graduate of MIT with a doctorate in electrical engineering, specializing in signal processing and control. Now, my research at MIT was in remote sensing. But here at GE, I've had the opportunity to apply the methods employed in my doctoral research and more generally my EE training to a wide variety. In here, I've had the opportunity to work in just about all of them, including aerospace, energy, aviation, manufacturing, and even healthcare. The real beauty of the Global Research Center is that we get to work on a wide variety of application areas. And it's one of the few environments where, ideas from aviation can make their way into healthcare and vice versa in sometimes surprising ways. Now, transportation is another industry, and it's no exception. The last few years, I've been part of the team that developed Trip Optimizer. So this is another software product that's having a real impact on the rail industry. Interestingly, it's bits and bytes, playing in an industry that's usually known for iron and steel, diesel engines, and mile-long freight trains. So what is Trip Optimizer? Well, Trip Optimizer can be described simply as a smart cruise control for freight trains. We'll get into the details as I proceed here. But it turns out that to make such a concept work entails quite a few interesting control and estimation problems. Now let me say at the outset that I'm only one member of the team that developed Trip Optimizer. This is a partial list here that I'm showing. It's emphasizing the most recent members. But many contributors here at the Research Center have made it possible. And the team is a global one, as you see, folks with whom we have just about daily contact. Also, the product is what it is because of the tight integration we maintain with members in our transportation business in Erie, Pennsylvania for this. What you're looking at right now is a picture of GE's Evolution locomotive. The Evolution locomotive is the platform on which we're launching this and other green technologies for trains. You know, even before Trip Optimizer, Evolution was already one of the most environmentally advanced locomotives. In fact, it was the first locomotive to meet new EPA emission standards, cutting emissions by up to 40% compared to the majority of diesel-electric locomotives in service today. Speaking in the near term, GE researchers are exploring new technologies to build on the Evolution platform to set even higher standards for emissions reductions and fuel efficiency. We're looking at several components of the locomotive engine, for example, including the fuel injection system and the alternators to find additional fuel savings. There's a team here that's working to make hybrid locomotives a reality and thereby recapture much of the energy that's currently lost to the atmosphere as heat. Now, drive strategy optimization is still another route to fuel savings and greener operation. So GE already offers technologies that automatically adjust engine parameters based on altitude and distribute horsepower most effectively among several locomotives on a given train to use less fuel. So Trip Optimizer is another step in the direction of both reducing costs for our customers and producing a greener, environmentally friendly product. Now, you know, all of this may seem surprising because this is kind of what most people's image of freight trains is. This is an image that comes from exposure to model railroads, etc. You know, the perception is that, you know, you have big hunks of, you know, iron locomotives with smoky chimneys. They're noisy, they're slow, they're not reliable, etc. So where's the high tech in all of this? And what do GE engineers have to do with all of this? I mean, is it just a matter of going around tightening bolts or something? Well, it turns out that's far from the truth, because if you look at what really matters to the railroads, you have the list that's shown here. So now a railroad will care about operating ratio. So what are their expenses as a fraction of their revenues? The drivers for that are getting the most productivity per person, getting the most out of each locomotive, you know, pulling harder with each locomotive, using less fuel per ton of freight. Secondly, return on capital. You want to use assets most effectively, most efficiently as possible. You want to keep your locomotives working and not idle. Growth in a growing industry. You want to get freight to the destination on time every time. And this is the way to gain share from their competitor, their chief competitor, which is trucks. Of course, safety is always a concern, keeping trains separated while not negatively impacting throughput, security and monitoring, being able to detect faults, etc., before they do damage, and of course compliance, meeting emission standards without compromising fuel efficiency. Now, all of these, in all of these, there's a role for it. Now, there's some interesting statistics. If you look at a comparison of the performance statistics for three different types of land vehicles, okay, we've got here a comparison of a fuel-efficient compact on the left, with a muscle car in the middle and a locomotive on the right. If you look at the Suzuki Maruti, okay, it's not, it doesn't have that much in the way of power, okay, 45 horsepower, develops about 46 foot-pounds of torque. Takes 20 seconds to accelerate to 60 miles per hour. Top speed 80. But what you get for all of that is a pretty fuel-efficient vehicle on the Suzuki. Much more torque. Can accelerate to 60 in 3.6 seconds. Much higher top speed. But look at the trade-offs in miles per gallon, only 8 to 12 miles per gallon. Now compare a locomotive. You've got an order of magnitude increase in horsepower, factor of 100 in torque that's developed, top speed 90. And when you look at MPG, the number looks unimpressive. However, let's take a look at this statistic, which is the freight haul efficiency, measured in ton miles per gallon. Here's where you see the locomotive really shine. The locomotive efficiency is 400 ton miles per gallon. Okay, almost a factor when you think about it. Because what it means is that if you've got a ton of freight, you can carry that freight 400 miles and use only a gallon of fuel. I think that's pretty astounding. So let's take a look at the fuel story a bit more and why it's important. Well, it's no surprise to anyone that fuel prices have been rising pretty rapidly the last several years. And for a while, the trend was about a factor 5 in 5 years, with more rises anticipated. Well, if you look at the operating expenses of the railroads, the typical railroad you see to the right there, fuel making as a group, North American railroads spent $12.2 billion just on fuel in 2008. Now, a typical locomotive uses about 350,000 gallons a year in diesel fuel. There are about 20,000 locomotives in service in North America. So what that means is that just 1% saved translates to 70 million gallons, or $221 million at 2008 prices. I think it's common knowledge that this current hiatus that we're seeing due to the recession is not long term. Once things start to pick up, I think you'll see fuel prices start to rise further. Control system to operate a train that uses fuel most efficiently and arrives on schedule. Now, along with that, you want to be flexible to adapt to change, and you want it to be easy to use. So all of that may seem simple enough, but it's actually quite hard. When you take into account things like the fact that the locomotives vary in their capability, including their fuel use, the traction they're capable of, the braking, train weights, and how the load is distributed on the train from car to car. That varies a lot. The track grades can vary and have a big impact on how you would operate a train. Curvatures, the condition of the track. There's also train dynamics. There's actually, the cars in a train are not rigidly coupled, so that means that when the locomotive at the lead starts to go, it actually takes some time before the last car starts to move. And that poses some complications when it comes to operating the train. Of course, you've got to operate the train being cognizant of other trains, traffic considerations. Now, all these things vary, and they're also uncertain. So those are where the challenges lie. Now let's take this concept of fuel-conscious cruise control and explore that a little bit. Well, everyone's familiar with a cruise control in a car. You basically set the speed to a fixed value, and the cruise control will maintain that value. Occasionally, you have to take it out of cruise when you hit the brakes, but otherwise you resume, and that's about it. On a train, you're seeing the situation here. Operators have to deal with speed restrictions, and these speed restrictions are extremely strict. It's very important that they be met, or you know, that besides compromising safety, there are stiff fines. So when you look at a speed restriction such as shown up above there, different drivers will take that speed restriction in different ways. And here I'm depicting how a few different operators might respond to that restriction. Well, only one of those curves is the optimal way to drive that train. And so what that means is that when you're not driving optimally, you're leaving fuel on the table. In addition to the less than optimal fuel use, it corresponds to higher emissions, trip variations, and even wear and tear on the track. So what Trip Optimizer does is it evaluates the entire route for the best way to operate the train, to give you the best fuel saving opportunities, and it plans the best speed at every point along the route. And after planning, it controls the throttle to that plan so that you get the trip the most efficiently operated each time, every time. So how does all this work? Well, it all starts with the railroad's data. Information arrives from dispatch, consisting of, you know, the origin and the destination of the trip, the makeup of the train, including its weight, its length, the number of cars, the number of locomotives, any temporary speed restrictions that apply for that particular day. All the data is transmitted via satellite to the onboard computer on a locomotive. The onboard computer will then plan the trip and provide that plan to the control system. And then the locomotive's microprocessors will use closed-loop control to regulate the speed to that plan. So this is what the driver sees. What you see depicted sort of with this light blue color here, is a representation of the grade that lies both ahead and behind the train. This thick white line represents the train. And so the driver gets a little bit of situational awareness. He knows what's ahead. There are times when part of the train may be cresting a hill, part of the train may be downhill, and the other half of the train might be on an uphill leg. The driver gets to see what's coming up. He's warned ahead of time about speed restrictions. At the speedometer, he's informed about the most efficient speed to have at that point in the trip. This is, of course, if the train is being operated. If the train is being operated in automatic mode, then the control system will automate. The throttle on a train is actuated through 8 discrete settings. These are called notches. And what you're seeing there is the notch that's currently set, and the notch that's actually dictated by the plan that's been computed. So the system allows a bit more in the way of situational awareness and can be operated in an advisory mode or in a full closed loop mode. taking a little bit of a look further under the hood, so to speak, you get what's depicted here. We already talked about the data flow. It'll arrive from dispatch. A trip planner will plan the trip, and then at that point, either a driver can take over and drive to that plan, or a closed-loop controller can execute the plan. So that issues a plan to the locomotive, and then we've got estimators on board that will tell where the train is and what its speed is at every given time, at every given moment of time. There's also estimators that are estimating the weight of the vehicle in the event that the parameters that were entered for the trip plan weren't correct. If that weight is estimated to go outside of a certain bound, then there's a replan that's generated. So focusing on the optimizer, which is really the core, there's some data that's semi-permanent. You've got information about the track. There's a rich track database that's used for that, to represent that. There's a database talk that characterizes the locomotive, including power, tractive effort, braking effort, and specific fuel consumption. Now, together with that, there's information that arrives about the current trip, arrival and destination times, your desired trip time. So the optimizer will take all that information in and compute an optimal plan for execution. Now, for a typical application, a 200-mile trip, people in optimization would appreciate some of these numbers here. There are about 900 spatial steps involved in this 200 miles, this first 200 miles from KC to LA. 1,800 decision variables need to be computed. There are over 5,000 constraints. And for a problem of this size, using the algorithm that we've developed, convergence is actually achieved in about 2 seconds on a 1 gigahertz desktop. And this is just to train folks on how to read the graphs you'll see here. We like to look at a profile of the grade as a function of distance. Here's the speed limit and the actual speed that's being that the train is going. And here, this is a graph of the notch. Anything above 0 means motoring, and below 0 is braking. So here's a view of what the basic intuition is with Trip Optimizer. What you can see is there's a speed restriction, and in the blue is what an engineer might do. The engineer, as he approaches the speed restriction, will often apply brakes and then remove them as the restriction is removed. Well, Trip Optimizer, it turns out, found a solution here that permitted brakes to be avoided altogether. And so the train was slowed down in the beginning, and then the momentum actually carried us through the speed restriction all the way through to the other side, completely eliminating braking. That braking avoidance translates directly to fuel. Now, most trains are operated for minimum time, but there's actually flexibility involved in Trip Optimizer. You're not locked into a specific plan. There's something called a fuel time curve, which means that basically you can operate the train for different average speeds. The slower you operate the train, the less fuel you use. And Trip Optimizer will actually allow you to choose from among these optimal solutions. So you're not locked into a particular solution. And most of the benefit, it turns out, can be achieved at the minimum time end of the curve. So what that translates to is if you give up just a little bit of time, in this case 16 minutes of additional travel time, there's actually a significant fuel benefit. So some examples here. This is a min time plan. You can see that to achieve this, to come under these speed restrictions, the drivers had to apply brake, actually Trip Optimizer applying brake in this case. But if we add 40 seconds to this min time, then Trip Optimizer comes up with a solution that will actually idle through that period. In another example, we can actually apply a constraint to avoid idle to keep the train stretched. And for just 2 pounds additional fuel, we can actually satisfy all constraints and save a significant amount of fuel. Here's what the results for a 200-mile trip might look like. Just to show you that all of this is pre-computed ahead of time. Speeds are always under the limit at all times. So here's our deployment status. Trip Optimizer was launched around the beginning of 2008. There have been about 25,000 track miles charted, and the system has run over 11 million revenue miles in that time. Our fuel savings are between 3 and 17%, and we've done this all without breaking any trains and having no negative velocity impacts on the network. We've gotten some press with the results we've achieved, and we've made some headlines both inside and outside of GE, in the trade press, and even some mainstream outlets. With time, we believe that computer-assisted train operation will basically become commonplace. So I hope that with these examples, we've shown you that high-tech locomotive is no oxymoron. There's actually ample evidence for problems that are very rich in challenges, and it's kept us busy here for a number of years now. I think with that, we'll open it up to some questions. Todd here has been collecting some of your questions, and we'll be glad to take some of them with the time we have left.
Hello, everyone. This is Todd again. If you can, just send me a quick note via chat or via the Q&A to send me your questions, and we'll try to get to them as much as we can in the time that we have. Okay, we do have one question on the Trip Optimizer, and I'll read it aloud and let Perry respond. For the Trip Optimizer, what optimization model and solver are used?
There isn't really a lot I can say about that without disclosing sensitive details, I'm afraid. But suffice it to say, we're using a numerical programming method, and it's a custom algorithm that's been developed here at GE, and we've been able to refine it to the point that we're able to run it and achieve computation times on the order of seconds, which has been a vital CTQ for us. Okay, we've got another question here. Is there any communication between the two functions, movement planning, trip optimizing, to maximize utilization of slack time in the movement plan for fuel savings in the trip plan? Well, as a matter of fact, if you've actually seized on one of the efforts that we're embarking on here, which is to integrate these two features to try to achieve even greater fuel savings. The way to think about it is with Movement Planner, we've got prior knowledge of meets and passes, And with Trip Optimizer's ability to flexibly manage varying trip times, we can make sure that we spend the least amount of time waiting. Because any time that you spend waiting means that you've actually consumed more fuel than you've had to. If there's a pass up ahead at which you're going to have to wait, you might as well take longer to get there because it will consume less fuel doing so.
I have another question. I'll turn this over to Srinivas on Movement Planner. Does the Movement Planner incorporate a train performance calculator?
A movement planner has information about train characteristics in terms of what is the maximum speed it can travel and what is the desired speed at which the train should travel. Other than that, when you say train performance, it's not very clear to me what train performance characteristic is. I believe it is the locomotive performance. I think it's addressed more in the Trip Optimizer product. But for the movement planner, what we know is we know the characteristics of the train in the sense that what is the maximum speed it can travel and what is the desired speed at which it wants to travel in different sections of the network. And there is okay. How does there's one other question. How does movement planner learn about the current train location and the speed? Okay, the movement planner, as I said, it is implemented in what is called a computer-aided dispatch system, and this system keeps track of the locations of the trains, in real time, and communicates that to the movement planner. So there is a big software system which keeps track of where the trains are and the current state of the signals, and all that information is communicated to the planner in real time. Can movement planner plan a crew swap? Yes, crew swap is one of the activities that it plans. Okay, this one. Okay, one other question on movement planner again. How do you resolve the inconsistencies between two adjoining territories? Okay, so if the way you would implement a movement planner on a rail network is we divide the network into multiple territories, and the way you resolve the inconsistencies is you make sure that at the boundary of the territories, the trains arrive in a pre-specified order. So as long as that order is maintained, you could match up two plans that are generated for two different territories at the boundary.
There's another question here. What are the effects of the Trip Optimizer on the engine's health? Do you consider as variables the effect of better driving, reducing damages on the engine? If you're asking whether we actually employ that in our optimization, we don't explicitly. However, we do expect that our plans will be easier on the tracks and easier on the engines. I don't think we've had the system in operation long enough to really quantify this and verify this, but we'll see that. I'm sure we'll be seeing evidence of this as time goes on. Another question: are railroads running the planner an optimizer themselves or contracting out to GE to run the program. Trip Optimizer is a product that is available and is used directly by our customers. We spend a little bit of time training the customers on its use, and after that, they use it themselves. For Trip Optimizer, for Movement Planner, it's the same. Another question is Trip Optimizer suitable or certified for positive train control systems? I know that Trip Optimizer is one of the stepping stones toward that. I am not an expert on that area. I'd have to defer to others on the project. But I believe that it is basically a stepping stone. One of the things that positive train control requires is very detailed track surveys and very detailed knowledge, real-time knowledge of train positions, etc. So it's not the whole solution, but it's one step in the process. Are the Trip Optimizer and Movement Planner commercially available to other customers? I'll speak about Trip Optimizer. Trip Optimizer is certainly available. We're right now it exists as a product on our Evolution locomotives, and I believe that plans are in place to make it more widely available as time goes on. But it's certainly been in use by several of the Class 1 railroads, and it's being fielded on still more.
Movement Planner also is a commercial product right now, and it is available for any railroad. And there was there were a couple of questions on the heuristic algorithm that we had developed for Movement Planner. Unfortunately, at this point, I'm not allowed to disclose any further details on that. Yes. Okay, there was another question on how much these products cost. For that, if you're interested, we can defer that to GE Rail. I mean, we don't know how much they cost.
Okay, I think we're actually up just a little bit over the 3 o'clock timeline. Just to let you guys know, first of all, I have a slide up on screen, ways that you can connect with GE Global Research. We have our website, of course, ge.com/research. Edison's Desk is a great blog that we have that our scientists contribute on, and we post blogs daily. You can also follow us on Twitter, YouTube, also Facebook as well. And I know we are going to make an audio transcript of this webinar available, via Edison's Desk, so look for that. But I want to thank Srinivas, and I want to thank Perry for taking the time to present on two exciting technologies that are making a difference for our railway system and for locomotives. And just thank you all for taking the time to join us for this software webinar. Thanks again, and have a great afternoon.